Well, happy Tuesday, everyone. Thank you for joining us for today's Snack and Learn. WSP is excited to present today's topic, the realities of electric aviation technology. We're going to dispel some truths and myths here today. As a reminder, there will be time for questions at the end, but please feel free to write any questions you think of in the question box as we go through the presentation. We'll try to answer those first at the end. Also, the presentation is available for download in the handouts box. Okay, so let's dig into it. Today's presenters will be myself, Jared Esselman, and my esteemed colleague, Mr. Bryant Cassett. Bryant is a dedicated systems engineer with nearly 3 years of experience at Electric Power Systems, EP Systems. He specializes in aircraft integration and charging infrastructure design. In his role, he excels in designing complex systems, defining aircraft and system requirements, developing high-level architectures, and conducting in-depth safety analysis. Bryant has emerged as a technical leader in the field of aircraft integration and charging infrastructure design. He has played a pivotal role in achieving the Diamond EDA-40's first flight, displaying his expertise in integrating electric propulsion systems in aircraft. His work includes designing a system integration laboratory, implementing energy storage systems, and shaping the roadmap for charging infrastructure design. Committed to pushing the boundaries of electric aviation, Bryant aspires to enable global travel for fully electric aircraft by providing affordable and convenient charging solutions. We're lucky to have Bryant with us this morning. Thank you, Bryant.
Appreciate that, Jared. So specifically, want to introduce Jared as well. So Jared began his career serving in the United States Air Force. He was a loadmaster on the C-17s and flew hundreds of combat missions into Iraq and Afghanistan. After serving in the Air Force, Jared worked in government affairs in the White House and graduated from Harvard University with a master's in public policy. Using his skill sets as policymaker and aviator, Jared worked as a director of government affairs for the Aircraft Owners and Pilots Association, the world's largest aviation association, and developed and passed aviation legislation and aviation policy in 26 different states. Most recently, Jared served as the director of aeronautics for the state of Utah, managing a system of 46 public use airports, a fleet of 6 aircraft, and a multi-million-dollar budget for aircraft capital improvements.
Well, thank you, Bryant. That's very kind of you. WSP is proud to serve aviation worldwide with innovative solutions for airports, airlines, and a variety of aircraft operators and services. We have over 1,500 airport programs with over 85 years of aviation industry experience and more than 700 staff ready to provide full service offerings at a single source. Now, for today's agenda, Bryant and I will separate the fantasy from the reality in electric aviation. We're going to cover the reasons why we're going to cover the reasons why electric aviation is such a hot topic in the industry. Now, rather than feeding you the hype and the headlines, we want to provide a very realistic set of expectations of aircraft, batteries, and airport infrastructure. As we highlight some of the questions we get asked about charging and power needs, we hope you will walk away feeling confident that your airport or sector of the industry can embrace this new technology as an alternate fuel source. So we're done with the agenda. Let's go on. There are several varieties. Go ahead to the next slide, Bryant. There are several varieties of electric aircraft being developed and flown today, and what I'm showing here is just a few of them. Uh, we're in a time that's not so dissimilar from when the Wright brothers were building their airplane. There were lots of ideas and lots of designs were attempted. Some were good and some were not so good. So right now, the predominant hype around electric aircraft is eVTOLs. Everybody's talking about Joby and Archer and Whisk and all the eVTOLs out there. And while these aircraft, they are flying today, I don't want to disregard that, but they're not ready for mainstream manufacturing. and it is not likely that you will see them landing at your airport in significant quantities anytime soon. However, small fixed wing trainers are far more likely first candidate for arriving at your airport. So, what's driving this movement? Well, many of you are probably aware that 100 low lead avgas is being phased out in the United States and in Europe, as well as many other parts of the world. And you probably also know that flight schools carefully track fuel burn rates since they consume more avgas than the typical recreational flight, simply due to the nature of training maneuvers being repeated over and over at higher than cruise power settings. Also, training aircraft are already being manufactured at scale. And for those that have already been manufactured, they can be retrofitted from their internal combustion engines to electric motors fairly easily. And with a high rate of engine overhauls, this can be an attractive alternative for flight schools. So you might see this a lot sooner at your airport and a lot more significant scale at your airport. So this has the potential to drastically reduce the cost of flight training. And since batteries do still have they have a limited range, right? That's one of the let's blow away the fantasy. The batteries have a limited range. So remaining in the airport environment for training is an acceptable and appropriate use for the current reality. So let's dig into it a little bit. Bryant, as a consultant, one of the questions I get asked often is, can an electric aircraft really even work? I mean, we talked about the limited range, we talked about they have to stay in the airport environment, but can they even really work?
And I guess the short answer really comes down to is that yes, they can work. We use batteries all the time in our daily lives. We use it in our phones, we use it in our laptops, we use it in our cars and trucks, and becoming more I guess, more available as electric vehicles on the road as well. So why not in our airplanes as well? So that's really comes down to the question that we're really asking. It's the same question that arose when some of these brands that are taking a spotlight, including Tesla and Rivian, came into the market. Were asked, there's like, can this really occur? And there was a lot of questions from a lot of people regarding this issue about whether or not they could actually make it work. And we're seeing those taking a comeback more and more into the industry now. And just like turning the wheels on a car, like you might see in a lot of these electric vehicles, we could also turn propellers and also generate thrust like you do in electric aircraft. Specifically for propeller-driven aircraft, like you see it here in the slides here, they're shown to be very suitable for the needs of for electrification. One of the aspects to consider, kind of separating the fantasy from reality a little bit here, is that when you're discharging from your batteries, you generate heat. So basically, as you're running your electrons through your motor, you're going to generate heat. And as you battery discharge, as well as when you recharge it, heat is going to be generated. Specifically, it happens with all batteries, but specifically with lithium batteries, it's a little more, potentially it has a little more hazards associated with it. Lithium is considered one of the best options right now for electrification because of its high energy density. I don't know how many of you have actually been able to hold like a lead acid battery. They're fairly dense and heavy, and they don't hold a lot of energy for how heavy they are. Lithium batteries, like what you have in your phone or like in some of these electric cars, do have better energy density, but the risk that we run is that when they get too hot, they have the potential of going to a thermal runaway. This is really as bad as it sounds. Basically, a thermal runaway is when it gets so hot that it basically self-feeds itself and then starts releasing extremely hot gases and a lot of times flames and shooting out debris, getting up to temperatures that can melt a lot of metals and basically consume a vehicle. To avoid hazards to the aircraft batteries do require special packaging. Specifically, lithium batteries require special packaging and cooling to ensure that thermal runaway really doesn't occur. Otherwise, we might be seeing aircraft catching on fire and come blazing out of the skies, or aircraft becoming engulfed in flames while on the ground while charging. These advancements in these packaging really come a long way and have allowed us to increase the safety, and so that this doesn't occur. We won't ever potentially see these, or very limited times that we'll actually see these occur, of major aircraft being lost due to thermal runaway.
Well, that sounds awful. Well, for those of us that are airport folks that aren't battery savvy, we want to avoid thermal runaway, and I'm glad to hear that the packaging, you and I have worked a lot on this, on the packaging itself. What do airport folks need to know about batteries? You talked about chemical cell a little bit, the chemistry of the cell a little bit. What do we need to know?
Well, there's no need to become a chemical engineer. I myself am not a chemical engineer, but understanding cell chemistry is somewhat similar to understanding the differences between aviation fuel, such as 100 low lead, and jet fuel. Um, Such as, like, if I mentioned a few different examples of different chemistries, like we have lithium ion. There's also nickel cadmium is used quite a lot inside the aviation industry, and there's lead acid, what you might see in like your car starter battery. Um, Really, it comes down to dictating what specific hazard, safety and hazard trade-offs you have associated with basically the energy density you're looking at. And these different cell chemistries also dictate specific safety and hazard procedures to address them at your airport. Now, nickel, cadmium, and lead acid are pretty common already in aircraft applications, and I'm sure a lot of you are already familiar with those type of batteries. They're non-volatile, and if they are, they're pretty um, they're very small in terms of their safety hazards as compared to lithium batteries. Lithium-based chemistries are making their entry into the aircraft industry, but they're still very new at this point in time. And so the safety and hazard procedures for addressing such fires or conditions where they fail is pretty immature at this point in time. There's not a lot of known procedures in place right now. Looking, we're trying to educate and help society understand a little bit more what those look like, especially for aircraft rescue and firefighting, or aircraft storage in extreme climates such as the tundra or hot desert conditions.
Well, in Utah, I can definitely understand hot and dry. Um, well, so if I'm an airport manager or if I'm an FBO manager, I'm going to have to recharge or refuel these at some point. What do I need to know about recharging?
Well, recharging really is just like refueling your vehicle, or any other aircraft in some ways, but there's some differences for sure. Essentially, we're just moving electrons basically from one location into the aircraft itself. We're just storing them within the battery. The major differences that we're looking at here is that we're generating heat as we charge the system, which is very different than fueling your aircraft. You're not generating heat when you're putting fuel in your tank. And the amount of heat that you generate from when you're charging the system really depends on how quickly you put it in. So if you're putting fuel in very, very slowly, you're not going to see a lot of heat generation. You're not going to see the electrons aren't going to generate a lot of heat. However, slow charging, as the name implies, is just like filling up your tank using a small spout, and so it's going to take a long time. Generally, it's um, one to at least 1 hour generally for the slow charging aspect without generating too much heat. Fast charging is kind of the new comeback that's coming into play both in the automotive as well as the aviation industry to make it a more viable option. But obviously with fast charging, like I mentioned earlier, that it generates a lot more heat. And so there's always the risk with that much heat, actually, that the batteries could go into thermal runaway because of the amount of heat they generate, as well as by doing this amount of fast charging, it does put some potential damage on the life of the battery overall. So to avoid these, generally for fast charging, we also have to provide provisions for cooling the battery, maintaining its temperature, and also allowing it to extend its life overall. So in the end, a lot of times what we'll see a charger with an associated cooling system to help either liquid cool or air cool the batteries while they're charging, which is an additional item to have to worry about while fueling aircraft.
Now,
So
so
go
go
ahead.
ahead, Brian. Sorry.
I was You had a question. Go ahead, Jared.
Well, I was just going to ask, is there a type of coolant we should use at the airports? I've heard
Generally, go ahead.
glycol, ethanol.
Yeah, so glycoethanol is a good mixture because of its um, in some environments you don't want it to freeze, so generally we do a 50-50 ethylene glycol um, to be able to cool the batteries during charging. Generally during flight, just because of the low draw, we don't necessarily see that, but yeah, so the airports will be the ones that are generally providing
Okay.
that coolant there.
So so it sounds like for this, I'm looking at the slide here, this 20 to 80%, it sounds like, if I'm a pilot today, I pull up and I say, hey, to the tabs. Not much different, 20 to 80%, right? To the tabs almost.
Hmm.
So, and I need to apologize for this next slide. It's a bit of a visual nightmare, but it's probably appropriate for what it's communicating. Bryant, tell us a little bit more about the charging process and how we take care of the battery itself through charging, because that's special and that's different
Hmm.
from just dumping fuel into my fuel tank.
Yeah, yep. So the actual dumping electrons into your batteries, I guess just to keep your same phrase there, it really requires a specific approach that we take. Um, and the approach really impacts our overall battery life. It also impacts our charge time. And so various different algorithms are required to, we've looked at a lot of different algorithms. You can see some of these at the bottom here under fast charging protocols. Looking at adjusting whether it's constant current, constant voltage, constant um, power, pulse charging, boost charging, stepped constant power charging. These different aspects really do impact your overall battery life. And one thing we've have seen overall is that when you do like a power charge, um, you overall can really see the benefits overall. And that's really, you don't need to know all the details of exactly how all these work. It's just good to know and understand how your aircraft's being charged to make sure that you're getting the best life out of your battery, that you are doing it in the fastest time possible without making a huge impact to your battery life. Generally, by adjusting these different protocols and charging algorithms, you could really potentially double or triple the life of your battery. As many of you know, with your cell phones, like over time, it doesn't hold a charge as well. Like when you first buy it, it might last 3 days of charge, and then after 2 or 3 years, you maybe have maybe a day at that point in time. And so there's a significant degradation in batteries over time, but also per cycle. And so trying to extend that really is going to save everyone money in the end. And so understanding that is going to be really impactful, I think, for the future moving forward on that.
Well, who doesn't like to save money, right? And it's important for aviation where for us to save where we can. Now, at this point, we talked a lot about the technology that's on the airplane itself, on the aircraft. But Bryant, let's talk about, where do I plug these in? Tell me about chargers.
Yeah, so chargers are basically just the way to fuel up with electrons. The difference is that we basically have electrons available everywhere we really need. You could plug something into a wall. You could just be able to charge your phone or whatnot. When it comes to electric aircraft, it really comes down to how fast do you want to charge your aircraft, because you could potentially plug your aircraft into a wall outlet and charge it. Something like that could take potentially a couple of days to charge it because the battery are generally probably several orders of magnitude larger than your phone battery or even your um, or twice as large as what you might see in a vehicle battery. And so you need basically infrastructure to be able to support that. It really comes down to is your mission needs and the different applications of chargers. There's really three basis of chargers. You can see some of these here. We have, for example, on the left here, this is a like a wall charger that is obviously bigger than you might see for your phone charger because you don't want to go several days without having your aircraft charged. But something like this is going to be slow and it's going to potentially be like an overnight charge. You might see like for like electric vehicles like a Tesla or Rivian in your garage overnight. You pull it into the hangar, you charge it overnight. You come in the morning, it's fully charged, and you're able to probably fly it once, come back in, charge it for the next day type thing. The next level is the mid level, as you see over here on the right in this example from Beta. Actually, it's a mid level charger. It charges a little bit faster. Might be something that FBO might use across the airport, might be able to maneuver, move around, plug into potential different outlets within different hangars or out on the ramp, and be able to charge up aircraft. It still is slower than you might expect for refueling a vehicle. It generally take probably 1 to 3 hours, probably depending on how quickly or how much provisions you have for charging. And then really the last one that's kind of where a lot of the focus and the hype is fast charging. These are the top level chargers. There's, as you can see at the bottom there, they're much larger format. A lot of times they're stationary, and they do require a substantial infrastructure upgrade because of the amount of power you're pushing out. Generally, what you look at for an aircraft hangar is somewhere in the range of probably, I think you could probably have maybe 5 kilowatts probably at most for a hangar without too much infrastructure upgrades. Generally, these chargers that we're looking at are upwards of like 250 kilowatts. So we're talking a very substantial upgrade in terms of size. And with that fast charging, we also have the associated cooling equipment, thermal management of those batteries that we're looking at. And really it comes down to is like, these are all very applicable. It just comes down to which, which mission that you want to use. Are you the type of person who just flies it once a day and just need a wall charger? Do you need it just a few times a day, so you need mid-level? Or are you like a flight training school where you just need very rapid turnaround? You're flying upwards of 6 flights a day, back to back to back, and so you need a fast charger, and what that looks like.
So real quick, as we're pushing time here, Bryant, real quick, what would these cost? Like, what am I looking at as far as cost?
Generally, the wall charger is probably, at least initially, it's going to be $2,000 to $5,000 that you see on the left there. The mid-level charger you see at the top right is going to be generally the $30,000 to $50,000, and then the fast charger we see at the bottom, a full system with the infrastructure upgrades, is generally around $250,000 for upgrading the system there.
That's actually not too bad. Now, you talked about infrastructure upgrades. What do I need? Do I really need to spend a whole bunch of money getting utility upgrades or for these chargers? What's the reality here? Because I hear like, oh, you got to get this new transformer, you got to get, maybe a new sub. I mean, it's just a lot of money to upgrade utilities. But what's the reality here?
Well, the reality is that you can, really depends on your mission that we're looking at. These infrastructure upgrades are really just increasing your pipeline size. It's just like you might have on a fuel farm. It's just a matter of how much fuel you're consuming on a regular basis. So if you're consuming a lot more electrons overall, then yeah, you're going to have to upgrade your pipeline potentially to have your charger. Now, to the point of a fuel farm too, there is an alternative, and I think that's kind of the difference here, is that the reality is that infrastructure costs a lot of money. It takes potentially hundreds of thousands of dollars and potentially up to a year to make those upgrades. And so to get up and running, it'll cost you a lot of money and a lot of time overall. And so the alternative to going the approach of basically doing like a 1 megawatt upgrade to your facility to look forward at be able to improve and have provisions for future aircraft coming into your airport is looking at the option of a microgrid with energy storage. And really, just as the name implies, a microgrid is like the main power grid, but it's an isolated grid from the main power grid, and basically allows you to manage the power internally, basically within that little microgrid, and specifically a DC microgrid that allows you to connect energy storage to it that acts as like a buffer or storage tank for your energy. So basically, you could have a small pipeline coming in, and then that pipeline just continuously sips off the grid and feeds this energy storage that's stationary or installed on the airport, as you see here on the left. And as the aircraft comes in and plugs in, it's pulling a lot of the energy from that battery. Basically, we have a big pipeline from the battery to the aircraft, and so in the end, it actually allows you more flexibility overall um, to future upgrades. You don't have to worry about these very costly and schedule intensive infrastructure upgrades. Instead, you purchase a system, you get it within 6 to 8 weeks, you put it in, bolt it down, install it with the rest of the system, you're up and running, and you really haven't really made any upgrades or major modifications to your connection to the grid overall. As well as it allows us really to um, integrate renewable sources such as solar or wind very, very easily within the system because the DC microgrid allows you to store a lot of the energy, just like you do from the grid, into those batteries and use them as needed.
So I don't, let's say I'm at a small airport and I don't have the money to get, I certainly don't have the money to upgrade my utilities. I may not have the money to go buy a microgrid, but where can I get started and what equipment can I get?
Yeah, there's a couple different approaches you could take. Is really we could go down to you don't really need to start with a very large like stationary microgrid. You can start with smaller microgrids, but the advantage of having a microgrid is that they're very easily expandable as you have a system. Um, in addition to like just starting out small, we also are looking at um, mobile microgrids. So as you see on the right here, this is basically a mobile microgrid. It's, as the name implies, instead of being a stationary microgrid that's installed on the airport, basically sipping off the power grid all the time, we have this mobile microgrid that basically acts like a fuel truck. It goes over, refuels potentially off of a charger on the airport or even down the road at a supercharger, like a Tesla supercharger, and basically receive those electrons and puts it in its own battery banks. And then it's able to drive right up to the aircraft on the ramp or in the hangar, and it's able to charge up your aircraft and cool them. So we could still do fast charging. We're able to still do quick turnarounds, and then the fuel or the electrons come to you in the end.
Well said, Bryant. Well said. I'm going to actually skip the next slide, buddy, and we're going to go on to. I hope for many of you that we have separated really the fantasy from the reality for electric aviation. You don't need to go up and upgrade your utility grid tomorrow. You don't need to become a chemical engineer or a battery engineer to know the difference. You already know the difference between 100 low lead and Jet A, and you'll know the difference or quickly learn the difference between fast charging and slow charging and what the mission is. And you'll learn the difference on what charges you need and where you can start small and grow slow. And I hope that we've done that for you today. Now, I've asked Brian a lot of questions, and I know we only have a very short amount of time, but I want to answer a couple of questions that came in through the chat. And specifically, I hope we answered your questions through the slides. So one of them is, how can the issue of deteriorating battery health causing expensive long-term maintenance costs be solved? Well, I hope we covered that on slide 11, Bryant. We did show maintaining and managing the state of discharge and the rate of recharge really does impact that battery health care. Um,
Yes, it's
are
very
there
significant.
constraints? What's
Yeah,
that?
go ahead. I said it's, yeah, it's very impactful. Go ahead.
Yeah. Are there constraints on flight time? Yes, yes, there are. You're not going to get the 4 hours that you might in a Cessna 172, but that's why we think the trainers are the first candidates because there is a constraint on flight time, and usually if you're doing a training flight, it's about 1.2 hours, and in the airport environment stays right there. Um, I'm going to go on to what are the typical outputs in kilowatts for the hanger wall charger, the slow charger, and the fast charger? I think we covered that. Bryant did mention the 250 kilowatts for the fast charger, which is about what the industry is aiming for right now, is 250 kilowatts for the fast charger per aircraft, I think.
And it really
Um,
depends on the aircraft size as well. As we get larger and larger aircraft, we're probably going to be looking at potentially megawatt chargers instead of 250 kilowatt
yeah,
chargers. So,
absolutely, absolutely. Okay, one last question here. I know we're a minute over, but with reduced noise levels and air pollution, do you think there will be more airfields near city centers? I think that's more of a question of zoning rather than fuel type. Yes, there will be less pollution, there will be less noise with electric aircraft. The question is, will the city center build an airstrip? That's the question. I think that comes down to zoning really and land use planning. Um, okay, and I think that's the last question we have time for today. If you have any further questions, please don't hesitate to throw them in the chat or in the question box. The webinar is available for download, or the handout is available for download. Please do that. Also, here's Bryant and my email and phone number. Text Bryant late at night, early in the morning. It's fine. Sorry, Bryant. Feel free to email us. Feel free to email us any questions. We'll be happy to answer them. With that, have a great day. Thanks, everybody.